Right now, light is landing on your skin. Every tiny piece of it carries energy. That energy came from somewhere. Where, exactly? Chase one single ray of light backward, and the trail gets strange fast. You will follow it into a trembling atom, then down into the crushing heart of the sun, where light born today may take tens of thousands of years to crawl free. You will stand beside a black hole that leaks light out of empty space. You will reach the oldest glow in the universe, still cooling after almost 14 billion years. Somewhere along this path, energy appears from nothing, then quietly vanishes, slipping through our fingers. If your mind likes being pulled apart like this, like the video and subscribe so the journey finds you again. We're about to trace light all the way back to its true source. Take a breath. We begin. Something is hitting your eyes right now, and it weighs nothing at all. Look at any glowing thing. A phone screen, a candle, a distant star. Each one is throwing tiny packets of light at your face, millions upon millions of them, every second. We call one of these packets a photon, and a photon is the strangest object in all of physics. Here is the first shock. A photon has no weight. You could gather up every photon streaming from the sun, pile them into a bucket, and the bucket would still weigh exactly the same. Light has no mass to sit still with. In fact, a photon can never sit still at all. The moment one is born, it flies at the fastest speed the universe allows, about 186,000 miles every second. It has never once slowed down. It cannot. Think of a bullet. A bullet needs a push to speed up and time to get going. A photon skips all of that. It leaves its source already at full speed, like a runner who is born mid-stride sprinting before its first heartbeat. So if a photon has no weight, what does it actually carry? Energy. Pure energy, wrapped in a tiny bundle. When sunlight warms your skin on a cold morning, that warmth is photons dumping their energy into you. When a plant grows, it is eating photons. When your eye sees colour, cells in the back of your eye are catching photons and turning them into signals your brain can read. Scientists spent hundreds of years arguing about what light really was. Some were sure it travelled as a wave, like a ripple spreading across a pond. Others swore it came in tiny pieces like a stream of sand. Both sides had proof. Both sides were stubborn. And it turned out both sides were right, which no one saw coming. Light behaves like a wave when it spreads and bends. Light behaves like a tiny piece when it strikes something and gives up its energy. A photon is both at once. Physicists have confirmed this thousands of times, and it still makes their heads hurt. One of the greatest minds of the last century admitted he spent his whole life trying to understand what a single photon is, and never fully cracked it. Picture a raindrop that is also a splash. That is close to the truth of a photon. A thing and a ripple sharing one body. And these photons are everywhere. Right now, trillions of them are passing through the room you sit in. Some came from the light above you. Some came from the sun 8 minutes ago. A few faint ones have been flying since the universe was young, crossing empty space for billions of years just to end their journey against your skin tonight. Every single one of them carries a small load of energy, and that is the question that will pull us across this entire journey. That energy did not come from nowhere. Something made it. Something paid for it. A photon is a delivery, and every delivery has a sender. So follow the light backward with me. Before we can find where its energy is born, we have to understand the one thing that decides how much energy a photon carries in the first place, and the answer is hiding inside its colour. Two photons can look completely different, and the only thing that separates them is how fast they shake. Hold that idea. Every photon wiggles as it flies like a jump rope snapping up and down. Some photons wiggle slowly, some wiggle at a furious blur. That speed of wiggling has a name. Scientists call it frequency, and frequency is the secret that decides everything about a photon. Here is the beautiful part. The colour you see is the wiggle speed. Red light is a slow, lazy wiggle. Blue light is a fast, tight wiggle. Violet is faster still. Slide from red to orange to yellow to green to blue, and you are simply speeding up the shake step by step. A rainbow is really a speed chart for light, laid out across the sky. Now the rule that runs this whole story. The faster a photon wiggles, the more energy it carries. A slow red photon is gentle. A fast violet photon punches harder. Same size bundle, very different power, decided only by speed. You can feel this yourself. Sit by a campfire. The red and orange glow warms you, and it feels soft. But the light you cannot even see, the fast wiggling light past violet, is the light that burns you. That is why you can get a sunburn on a cloudy day when the air feels cool. Invisible high-energy photons from the sun are slamming into your skin and breaking things inside your cells. Your eyes never saw them coming. Scientists gave these invisible fast photons a name, ultraviolet, which just means beyond violet. Keep speeding up the wiggle, and you reach X-rays, the light that passes through your body to photograph your bones. Speed up more and you hit gamma rays, the most violent light in existence, born inside exploding stars. Now go the other way. Slow the wiggle below red, and you reach infrared, the warm glow your body gives off in the dark. Slower still, and you get microwaves, cooking your food. Slowest of all are radio waves, so gentle and stretched out that a single one can be miles long, longer than a whole city. So the full family of the light stretches from soft radio waves you could almost surf on to savage gamma rays that could kill you. And every member is the same thing, a photon. The only difference between the light that carries a song to your radio and the light that comes screaming out of a dying star is how fast it shakes. There is a clean formula behind this, worked out by a careful German scientist named Max Planck more than 100 years ago. His rule lets you take any photon's wiggle speed and calculate its exact energy. Physicists have tested it endlessly, and it holds every single time. It sits at the root of all modern physics. Picture a piano. A low note is a slow, deep string. A high note is a fast, tight string. Light works the same way. Red is the bass note of the universe. Gamma is the highest scream at the top of the keyboard, so we know what decides a photon's energy. But knowing how much energy it holds does not tell us where that energy came from. To find the source, we have to shrink down and step inside an atom, where most of the light around you is truly born. Deep inside every atom, a tiny prisoner is about to fall, and its fall makes light. Zoom into anything around you, your hand, the air, a chunk of metal. Everything is built from atoms, and atoms are almost entirely empty space. In the center sits a tight core. Around it, at a wild blur, race even tinier pieces called electrons. These electrons are what make most of the light you see. Here is the strange rule they follow. An electron cannot circle the core at just any distance. It can only ride at certain fixed heights, like a climber allowed to stand on the rungs of a ladder but never in the gaps between them. A low rung is a calm, low-energy spot. A high rung is a jumpy, high-energy spot. Now give the atom a jolt. Heat it, zap it with electricity, or hit it with light. One of those electrons soaks up the energy and jumps to a higher rung. It is now excited, holding extra energy it does not want to keep. It sits up there, unstable, like a ball balanced on a shelf. Then it falls. The electron drops back to a lower rung, and the exact moment it falls, it has to get rid of the extra energy it was carrying. So it spits out a photon, a flash of light, born in an instant, carrying away precisely the energy the electron just lost. Big fall, high energy photon, a bluer colour. Small fall, low energy photon, a redder colour. The size of the drop picks the colour of the light. This one trick explains almost every glowing thing you have ever seen. A neon sign glows because electricity kicks electrons up, and they fall back down spitting red light over and over, billions of times a second. Fireworks burst in colour for the same reason. Each metal in the powder has its own ladder with its own rung spacing. Copper drops give blue-green. A metal called strontium gives deep red. That is why a chemist can read a fireworks recipe just by watching its colour explode overhead. Scientists have confirmed this so precisely that they can name what a distant star is made of without ever touching it. They catch the star's light, spread it into a rainbow, and read the exact colours glowing or missing. Each element leaves its own set of colour fingerprints. We learned what the Sun is built from 93 million miles away, just by studying the light falling from its electrons. Picture a set of stairs where the steps are odd heights. Drop a ball down a tall step and it lands with a loud bang. Drop it down a short step and it lands with a soft tap. Each atom is a staircase with its own step sizes, and each drop rings out its own note of light. So we have found the birthplace of most of the light around you. It comes from electrons falling down ladders inside atoms, tossing off photons as they land. But this only pushes the mystery one step back. The electron had to climb up before it could fall. Something lifted it. Something poured energy into that atom first. So where did that energy come from? Follow the light one layer deeper, and the answer starts to sprawl out in every direction. Every photon you have ever seen is really borrowed energy, and now we hunt down the lender. An electron falls and makes light. Simple. But that electron had to climb first, and climbing costs energy. So the real source of the light is whatever gave the electron its boost. Trace it back, and you find a handful of usual suspects. The first suspect is heat. Everything warm is secretly shaking. Inside a hot object, atoms slam into each other like a crowd shoving in a packed hallway. Every collision can knock an electron up a rung. Then it falls and makes light. This is why things glow when they get hot enough. The hotter it is, the harder the atoms crash and the more light pours out. A stove coil turns from black to dull red to bright orange just by shaking faster. The second suspect is electricity. Push a current through a gas, and the flow of charge smacks into atoms and lifts their electrons. This is the whole trick behind a glowing sign or a bright tube. You're paying an electric company to kick electrons up ladders so they can fall back down and glow for you. The third suspect is light itself. A photon can be caught by an atom and hand its energy over, lifting an electron. Later that electron falls and makes a new photon. So light can create light, passed along like a baton in a relay race. This one detail will matter enormously later in our journey. Notice the pattern. In every case, the light was already paid for by something else. The energy did not appear inside the atom on its own. It was delivered, heat delivered it, electricity delivered it, older light delivered it. The atom is a middleman. It takes energy in one form and hands it back out as a photon. Here, a deep and simple law of the universe shows its face. Energy is never made from nothing, and it can never be destroyed. It only changes its coat. The chemical energy in wood becomes the heat of a fire, which becomes the light of the flame. The energy inside a power plant becomes electricity in a wire, which becomes the glow of a bulb. At every step, the same energy just wears a new outfit. Scientists have tested this law harder than almost any idea in science, and it has never once failed inside a lab. You cannot cheat it. You cannot squeeze free energy out of empty hands. Every glow has a bill, and something always pays. Picture a bucket brigade fighting a fire. One person fills a bucket at the well, and it passes hand to hand until water hits the flames. No one on the line creates the water, they only move it along. Energy travels the same way, from the well of some source, through the atom, out into the light that hits your eye. So the light in your room is a long chain of handoffs stretching back to some original source of power. For a bulb, that source is a wire and a distant power plant. For a fire, it is the chemical energy locked inside wood. But the grandest lender of all hangs in the sky. It floods the entire Earth with light every single day, and it runs on a fuel unlike anything on our planet. To understand where a sunbeam's energy is truly born, we first have to understand why anything warm glows at all. Right now, in total darkness, your own body is glowing, and special cameras can see you shine. Every object warmer than the coldest possible cold is giving off light. You are. Your desk is. A cup of coffee, a sleeping cat, a brick wall at night. All of it glows. You just cannot see most of this light, because your eyes are built to catch only a thin slice of all the light that exists. Here is why warm things shine. Heat is motion. Inside anything warm, the atoms and their electrons are jiggling and bumping. Every time a charged piece like an electron shakes or gets jostled, it throws off a little light. Warmer means faster jiggling, which means more light, and higher energy light. Cold means slow jiggling and faint gentle light. At room temperature, your body glows in infrared, the slow wiggling light just below red that human eyes cannot see. Soldiers use night vision goggles to catch exactly this glow. A person hiding in pitch black still lights up like a lantern to the right camera, because a living body runs at about 98 degrees, far warmer than the cool night around it. Now start heating something and watch the glow climb the rainbow. A metal bar in a forge sits dark at first. Push it into the fire and it begins to smoulder a dull red. Hotter and it brightens to orange, then yellow. Hotter still and it burns white, throwing off every colour at once. The colour of a hot object is a thermometer. A blacksmith can read a metal's temperature just by its shade, without any tool at all. The stars run on this same rule, on a giant scale. A cool star glows red. Our sun burns yellow-white, with a surface near 10,000 degrees. The hottest stars blaze blue, running many times hotter than the sun. So the colour of a star tells you its temperature from trillions of miles away. Astronomers glance at a star's shade and instantly know how hot it burns. Blue is furious. Red is calm. Scientists have confirmed this link between heat and light down to fine detail. There is even a strict rule that ties an object's temperature to the exact peak colour it glows. It works for a candle flame, a human body, a lump of iron and a star, all with the same math. The universe uses one recipe for everything warm. Picture a crowd in a stadium doing the wave. When people move slow and sleepy, the wave is low and lazy. When the crowd gets fired up and moves fast, the wave grows tall and sharp. Heat is the crowd's energy. Light is the wave they throw. The more excited the crowd, the wilder the wave. So the warmth of a fire and the glow of a fire come from the same thing. Shaking. And the source of that shaking in a fire is a violent event happening down at the level of the atoms as they rip apart and rebuild. That event has a name you have known since childhood. Fire. We use it, cook with it, fear it, and love it. Yet almost no one can say what a flame actually is, or where its light is truly born. So step close to the fire with me and watch what is really happening inside the light of a burning flame. A flame is one of the oldest things humans ever tamed, and most people have no idea what it really is. Light a match and stare at the flame. It looks solid, almost alive, dancing on the wood. But you cannot touch it, cannot hold it, cannot cut a piece off. A flame is a place where something powerful is happening, made visible by heat and light. Here is what fire truly is. It is a chemical reaction, a fast and hungry one. Wood, wax and gas are all packed with a fuel that loves to grab oxygen from the air. Normally they sit still, holding that fuel locked away, but give them a spark of heat, and the fuel starts snatching oxygen and tearing itself apart. When it does, it releases a burst of energy that was stored inside, waiting. Think of the fuel as a wound-up spring. Every bit of wood holds tiny springs coiled tight, full of stored energy. Fire lets those springs snap loose all at once. The energy that comes flooding out is what we feel as heat and see as light. A campfire is really the sound of 1 billion tiny springs releasing at the same time, so where does the light come from? 2 places. First, the reaction heats up tiny specks of soot, floating in the flame until they glow, the same way the metal bar glowed in the forge. Those glowing specks give a flame most of its warm orange colour. Second, some of the reaction throws off light directly, as excited pieces fall back down and spit out photons. This means the light of a candle is chemical energy turned into glow. The wax holds the energy. The flame is the moment of release. When a candle burns down over an evening, you are watching stored energy leave the wax and fly off as heat and light into your room. The wax gets lighter as it burns, because its energy is literally flying away. Different fuels burn in different colours, because different fuels release different amounts of energy. A wood fire glows warm orange. A gas stove burns blue, because gas burns hotter and cleaner, with almost no glowing soot. Campers know that a blue flame is a hot flame, and an orange flame is a cooler, dirtier one. The colour is a report card on the burn. Fire changed everything for our ancestors. It let them cook, which unlocked more food energy from every meal. It kept them warm and safe through the dark. Some scientists believe that taming fire is one of the reasons human brains grew so large. A hungry chemical reaction, glowing in the night, may have helped make us who we are. Picture a warehouse packed with coiled springs, all touching. Flick one loose and it strikes its neighbour, which strikes the next, and a wave of snapping races through the whole room in a flash. That runaway wave is a flame, spreading through fuel, releasing stored energy at every step. So a fire's light is paid for by chemistry, by the energy stored inside a fuel long ago. For wood, that energy came from a tree, which drank it from sunlight over many years, so even a campfire is really old sunlight, escaping at last. We keep circling back to the same trick though. Heat something enough and it glows. Humans took that trick and built a machine to light the whole world with it, using a thread of metal thinner than a hair. For most of human history, when the sun went down, the world went dark, until one thin thread of metal changed everything. For thousands of years, people fought the night with fire, candles, oil lamps, torches, all of them the same trick, a small controlled flame, smoky and dangerous and dim. Then, a little over 100 years ago, inventors chased a wild idea. What if you could make light with no flame at all? What if you could make heat glow using only electricity? Here is the idea behind a glowing bulb. Take a very thin thread of metal and run electricity through it. Electricity is a flood of moving charge, and as it shoves through the narrow thread, it bumps and drags against the metal, like water forced through a clogged pipe. All that bumping makes the thread heat up. Push enough current, and the thread gets so hot it starts to glow, climbing the same colour ladder as the metal bar in the forge. The thread inside an old-style bulb is made of a metal called tungsten, chosen for one reason: it can get insanely hot without melting. Inside a working bulb, that thread runs at around 4,500 degrees, hotter than most lava on Earth, glowing bright white. It sits inside a glass bubble, with the air pumped out, because if air could reach it, the blazing thread would burn up in a puff. So an old-fashioned bulb is a tiny piece of metal, held at a temperature close to the surface of a cool star, throwing off light because it is so violently hot. The electricity does not become light directly, it becomes heat first. The heat becomes the glow. Here is a catch that drove engineers crazy for decades. This kind of bulb is terribly wasteful. Out of all the energy you feed it, only a small slice, around 1/10, comes out as visible light. The rest pours off as invisible heat you cannot even see. That is why an old bulb gets hot enough to burn your fingers. You are paying for light, but mostly buying warmth. That waste is why the world has switched to newer lights that skip the heat and make light in a smarter way. Those newer lights barely get warm at all, and we will reach the trick behind them very soon. Picture a crowded turnstile at a stadium. When only a few people push through, everything moves smoothly and stays cool. But cram thousands of people shoving through that one narrow gate, and the friction, the bumping, the struggle makes the whole thing heat up. Electricity forced through a thin thread does the same thing. The struggle to squeeze through becomes heat, and the heat becomes light. So the light from an old bulb is paid for by electricity, which came from a power plant, which likely came from burning fuel or spinning a turbine far away. Trace the glow of a single reading lamp backward, and you often end up at a river, a gust of wind, or a lump of coal, miles from the room you sit in. We have now seen light born from falling electrons, from heat, from fire, and from a struggling wire. Every one of them ran hot, but nature figured out something we took ages to copy. Some living things make light that is almost completely cold, glowing in the deep dark of the ocean without a spark of heat. 2 miles down in the ocean, where sunlight has never reached, the darkness is full of living lights. Go deep enough into the sea and you leave the last of the sunlight behind. Below about half a mile, the water turns pitch black, colder than a refrigerator, crushing and silent. You might expect it to be empty. Instead, it glows. Tiny lights drift and flash all through this black world, made by living creatures. Scientists believe most animals in the deep ocean can make their own light. It may be the most common way of glowing on the entire planet. This living light has a name: bioluminescence, which simply means light made by life. A firefly blinking in a summer yard is doing it. So is a glowing jellyfish, a deep-sea shrimp, and a fish with a lantern dangling over its own mouth. And here is the wonder of it. This light is almost perfectly cold. Remember, every glow we have seen so far ran hot. Fire, bulbs, glowing metal, all of them burned. A firefly breaks that rule completely. You can hold one in your hand and its light gives off no warmth at all. If a firefly made light the way a bulb does, wasting most of its energy as heat, it would cook itself alive in an instant. So how does life do it? With chemistry, run gently. Inside the creature sit two special ingredients. One is a molecule that stores energy and loves to react. The other is a helper that speeds the reaction up and controls it. Add a little oxygen, and the two react in a careful, quiet way. The energy released comes out almost entirely as light, with barely any heat wasted. It is the cleanest light-making known to science. A firefly turns nearly all its energy straight into glow. Life uses this cold light for everything. An anglerfish dangles a glowing lure to trick prey close to its teeth. Some squid blast out a cloud of glowing goo to blind a predator and escape. Certain tiny sea creatures light up the ocean surface so that boats leave trails of blue fire in the water on dark nights. People sail through glowing waves and feel like they are moving through a dream. The fuel for all of it is food. The creature eats, breaks down its meal, and stores some of that chemical energy inside its light-making ingredients. When it flashes, that stored food energy leaves as light. So a firefly's glow is powered by its dinner, the same way your muscles are powered by yours. Picture two chemicals in a beaker that you mix together, and instead of getting warm, the liquid begins to shine with an eerie glow, cold to the touch. That is the trick a glow stick uses at a concert, and it is the same trick a firefly uses in the dark. Bend the stick, the two chemicals meet, and light pours out with no heat at all. Scientists have even borrowed this glow for their own tools. They now use the light-making genes from these creatures to make cells light up in a lab so they can watch disease spread or track a gene switching on. Life's own lanterns became a scientist's flashlight. So far, every light we have met needed a fresh source of energy poured in, a fuel or a current. But there is a stranger kind of glow, one that steals its energy from light that already exists, and hands part of it back in a brand new colour. Shine a certain hidden light on the right rock, and it bursts into colours that seem to come from nowhere. Walk into a dark room and switch on a special lamp, one that gives off mostly invisible light past violet. Suddenly certain things around you erupt in glowing colour. A white shirt blazes, a poster lights up, a plain grey scorpion turns electric blue. It looks like magic, as if these objects are making light from thin air. They are catching invisible light and handing it back in a colour you can see. This trick is called fluorescence. Here is how it works, step by step. That special lamp is pouring out high-energy photons, the fast, wiggling kind beyond violet that your eyes cannot catch. When one of these invisible photons strikes the right material, it gets swallowed. Its energy kicks an electron up the ladder just as we saw before. But now something clever happens on the way back down. Instead of falling in one big jump, the electron comes down in a couple of smaller steps. It sheds a little energy quietly as heat, then drops the rest and spits out a photon. Because that leftover drop is smaller than the original leap, the photon it makes is weaker, slower wiggling, and lower energy. And lower energy light is a colour you can see. So an invisible photon goes in, and a visible glowing photon comes out. The object seems to shine on its own, lit by light you never knew was there. This is why a highlighter pen seems to almost burn on the page. The ink drinks in invisible light from the room and pours it back out as that intense glowing yellow or pink. It catches light you cannot see and gifts you a colour you can. Nature loves this trick. Scorpions glow blue-green under that hidden light, and scientists still argue about why. Some think it helps them sense light, others think it confuses prey, and honestly, no one is fully sure yet. Certain corals glow in brilliant colours deep underwater. Some minerals that look dull and grey in daylight blaze red, green, and orange the instant that special light hits them, as if a secret painting was hiding inside the stone all along. Notice the key difference from a firefly. A firefly builds its light from scratch, using food energy. A fluorescent rock builds nothing on its own. Cut off the incoming invisible light and the glow dies at once. It only shines while it is being fed light from outside. It is a borrower, catching photons and passing them along in a new colour, keeping a little energy as a fee. Picture a person catching a fast, heavy ball, stumbling back a step from the force, then gently tossing back a lighter, slower ball. They kept a bit of the energy in that stumble. The ball that comes back is softer than the one that came in. Fluorescence does the same thing with light. It catches a hard, fast photon and tosses back a soft, slow one, pocketing the difference as heat. This idea of light triggering an atom to release new light is about to explode into one of the most powerful inventions ever made. Because if you can get atoms to spit out light on command, and get them all to spit out the exact same light at the exact same moment, you can build a beam so perfect and so focused it can cut through steel. In 1960, scientists switched on a machine that made a kind of light nature had never once produced on its own. Ordinary light is a mess. A flashlight, a bulb, the sun. All of them throw light out in a jumble. Many colours spreading in every direction, wiggling out of step with each other, like a huge crowd all shouting different words at once. It works fine for seeing, but it is chaos. Now imagine forcing every photon to be identical, same colour, same direction, all wiggling up and down in perfect lockstep, like a marching army instead of a mob. That perfect, obedient light is a laser. Here is the trick that makes it, and it grows straight out of the last chapter. Remember how a photon can strike an atom and get swallowed? There is a mirror image of that event. If an atom is already excited, sitting up on a high rung, and a passing photon of just the right energy zips by, that photon can tickle the atom into falling early. When it falls, it spits out a new photon. And here is the beautiful part. The new photon comes out as a perfect twin of the one that triggered it. Same colour, same direction, marching in step. Now you have two identical photons where you had one. Those two each strike more excited atoms and make two more twins, then 4, then 8. In a flash, a storm of perfectly identical photons is racing back and forth. A scientist named Albert Einstein predicted this exact effect decades before anyone built a machine to use it. To pull this off, you need a crowd of atoms all pumped up and ready, holding their energy, waiting to fall. You feed them energy first with electricity or a bright flash. Then you trap the growing light between two mirrors so it bounces back and forth, triggering more and more twins on every pass, building into a roaring flood. One mirror lets a sliver of that light leak out. That escaping sliver is the laser beam. Because every photon in that beam is identical and marching together, the beam stays razor thin and travels incredibly straight. Scientists once bounced a laser off a mirror left on the moon by astronauts. The beam crossed roughly 240,000 miles of space, struck a target the size of a suitcase, and bounced back. A flashlight would spread into useless fog after a few hundred feet. That tight, orderly power is why lasers can do things no ordinary light can. A strong enough laser can slice through metal because all its energy is packed into a pinpoint. A gentle one reads the code on your groceries, plays music off a disc, and carries the whole internet as pulses of light down glass threads under the ocean. Picture a stadium crowd doing the wave, but sloppy, with people standing at random times. Now picture the same crowd trained to rise at the exact same instant, again and again, a clean, powerful wall sweeping around the stands. Messy light is the sloppy crowd. A laser is the trained one. Same people, vastly more power, just from perfect timing. Every source of light so far has lived on Earth, fed by fire, food, or a wall socket. Now we lift our eyes to the greatest light maker of them all, a furnace so vast and so hot it has lit our world for billions of years, running on a fuel that turns matter itself into pure energy. At the heart of the sun, the same force that could destroy a city keeps our whole world alive. Look up at the sun safely for just a heartbeat. It looks calm, a steady yellow lamp in the sky. But that gentle glow hides the most violent furnace in the solar system. The sun is a giant ball of gas, so huge you could pour more than 1,000,000 Earths inside it, and all that gas presses down on the centre with unimaginable weight. That crushing squeeze creates the exact conditions for something extraordinary. Deep in the sun's core, the temperature reaches around 27 million degrees. The pressure is beyond anything we can build on Earth. Down there, the gas is squeezed so hard that the tiniest pieces of matter, the cores of hydrogen atoms, get slammed together and stick. This sticking together of tiny cores is called fusion, and it is the true engine of the sun. Here is what happens in that fusion. 4 cores of hydrogen, the lightest, simplest stuff in the universe, get crushed and welded into 1 core of helium, the next lightest. Simple enough. But when scientists weighed the result, they found something that shook physics to its roots. The new helium core weighs a little less than the 4 hydrogen cores that went into it. A tiny sliver of matter has gone missing. That missing matter did not vanish for nothing. It turned into pure energy. It flew out as light. Every time the sun fuses hydrogen into helium, it converts a whisper of matter directly into a blast of energy. And the sun does this an unthinkable number of times each second. Every single second, the sun turns about 4 million tons of its own matter into pure energy. 4 million tons gone, every tick of the clock, becoming the sunlight that warms your face. That number is almost impossible to feel, so hold this picture. Every second, the sun destroys more mass than the weight of a small mountain and pays it out as light and heat flooding across the solar system. It has been doing this for over 4 billion years, and it has enough fuel to keep going for billions more. Here is where the sunlight on your skin is truly born. The real source is matter itself being deleted and reborn as energy in the crushing core of a star. The warmth of a summer day is the ghost of vanished matter carried to Earth as light. Scientists have confirmed all of this. We have caught ghostly particles that stream straight out of the sun's core, proof that fusion is running right now, deep inside. We even try to copy this process here on Earth, building machines to squeeze hydrogen and force it to fuse, chasing a limitless source of clean power. So far, the sun still does it far better than we can. Picture 2 lumps of soft clay. You smash them together with all your strength into 1 lump, and in the smashing, a spark of pure energy leaps out, and the final lump weighs a hair less than the 2 you started with. That missing hair became the spark. Fusion is that smash, run trillions of times a second, at the centre of a star. But this trade, matter turning into energy, follows a strict and famous rule. 1 short equation controls exactly how much energy you get when matter vanishes. And that single line of math is the most powerful idea in all of science. 1 short line of math scribbled by a clerk in a patent office revealed that matter and energy are secretly the same thing. More than 100 years ago, a young man worked a quiet desk job reviewing inventions. In his spare hours, he thought about light, space, and time, and he changed the world. His name was Albert Einstein, and he uncovered a secret hiding in plain sight. Matter and energy, which look completely different, are really 2 forms of one thing. You can turn one into the other, and he wrote down the exchange rate. That exchange rate is the most famous equation ever written. It says the energy locked inside any lump of matter equals its mass multiplied by the speed of light, and then multiplied by the speed of light again. The details matter less than the shocking meaning. Multiplying by the speed of light twice means multiplying by a gigantic number. So even a crumb of matter holds a monstrous amount of energy, if you could fully release it. Let that size settle into a real picture. The matter in a single raisin, if turned completely into energy, could power a city for a day. A raisin. The matter in a paperclip could rival the blast of a powerful bomb. Matter is frozen energy, packed unbelievably tight, and it almost never lets that energy out. It just sits there, quiet, holding a hidden ocean of power inside every gram. This is the rule that lets the sun shine. When the sun fuses hydrogen, and a sliver of mass goes missing, this equation tells you exactly how much energy comes out. and it comes out as a flood because that missing mass gets multiplied by that enormous number. A little vanished matter, a vast burst of light. The equation and the sun agree perfectly every time we check. It also sets up something even more extreme, waiting further along our journey. If a little vanished matter makes a huge burst of energy, what would happen if matter vanished completely, all of it, turned fully into light? That would be the most efficient release of energy the universe allows. Hold that thought. It is coming. For most of history, people thought matter and energy lived in separate worlds. Rocks were rocks. Heat was heat. Einstein tore down the wall between them. He showed that a rock is a storehouse of sleeping energy and that energy can freeze into fresh matter. The two are partners, always able to trade places following his simple rule. Scientists have tested this idea in more ways than almost any other, and it stands rock solid every time. Nuclear power plants run on it, releasing the energy hidden in heavy matter. The sun and every star run on it. The equation is woven into the deepest fabric of reality. Picture a bank vault the size of a marble, and inside it sits more money than a whole country earns in a year. The marble looks tiny and ordinary. Only someone who knows the secret understands the fortune packed inside. Every bit of matter is that vault. Einstein simply handed us the key and told us the exchange rate for what lies within. So the sun's light is born from vanished matter, cashed in through Einstein's rule. But that light does not fly straight out of the sun into space. It is born deep in the core, and it faces a nightmare journey to escape, one that can take longer than the whole history of the human race. A single ray of light born in the sun's core today may not escape into space until humans have long been forgotten. We think of sunlight as instant. Flip on the sun and light pours out. And the trip from the sun's surface to your eyes really is quick, only about 8 minutes across 93 million miles of empty space. But that 8-minute dash is the easy final sprint of a journey that began an almost unimaginable time before. Here is the problem a newborn photon faces. It is born as a fierce burst of energy deep in the sun's core, right where fusion happens. To reach freedom, it has to travel from the center to the surface. In empty space, that trip would take about 2 seconds. But the inside of the sun is the opposite of empty. It is packed so densely with matter that the photon cannot fly straight for more than a hair's breadth before it slams into something. Every time the photon hits a particle, it gets swallowed and spat back out in a random new direction. Forward, sideways, even backward. It takes a step, crashes and gets flung off a different way. Then again, and again, billions upon billions of times. The photon is staggering through a mob bounced around helplessly, drifting outward at a crawl. Scientists call this a random walk, and there is a perfect picture for it. Imagine a person leaving a bar after far too many drinks trying to walk home. They stumble one step forward, lurch sideways, wobble back, weave in a new direction over and over. Even though every step is a normal size, they barely get anywhere, because their direction is pure chaos. A photon in the sun is exactly that stumbling walker. Taking a mind-bending number of tiny random steps to cross a distance light could normally clear in a blink. So how long does this drunken crawl actually take? The honest answer is that scientists argue about the exact figure, because it depends on the fine details inside the sun. Many estimates land in the range of tens of thousands of years. Some calculations push it far higher, past 100,000 years. The precise number is still debated, and different models give different results. Sit with what that means. The sunlight warming your face today may carry energy that was born in the sun's core back when our ancestors were first learning to make tools before cities, before writing, before recorded history of any kind. That energy stayed trapped inside the sun, bouncing in the dark, for longer than human civilization has existed. It finally reached the surface, made its 8-minute leap across space, and landed on you. As the photon crawls outward, it slowly changes. In the core, it was born as a savage high-energy ray, the kind that would tear through your body. But with each bounce, it hands off a little energy, cooling and softening on its endless climb. By the time it reaches the surface and escapes, it has mellowed into the gentle, visible sunlight we can safely enjoy. So the light on your skin is old, patient energy, freed at last after an epic imprisonment. It escaped the crush of the core and reached the calm surface. From there it flies free into space. But some of that light is about to reveal a fiercer secret. When electrons deep inside heavy atoms take a violent enough fall, they make a light powerful enough to pass straight through your flesh and photograph the bones beneath. In 1895, a scientist stumbled onto a mysterious new ray, and the first thing he photographed with it was the bones inside his own wife's hand. His name was Wilhelm Röntgen, and he was tinkering with electricity in glass tubes when he noticed something impossible. A screen across the room began to glow even though it was shielded. Some invisible ray was shooting out of his equipment, passing through solid objects and lighting up the screen. He had no idea what it was, so he called it an X-ray, using the letter scientists use for an unknown. The name stuck. Then he did something that made history. He placed his wife's hand on a photographic plate and beamed his mystery ray through it. When the picture developed, it showed the dark shadows of her bones and the pale ring of her wedding band, with the flesh nearly invisible. She looked at the image of her own skeleton and said she had seen her death. No living person had ever glimpsed inside their own body while still perfectly healthy. So what is an X-ray really? It is light, the same family as the glow of a candle and the colour of the sky, just far up the ladder, wiggling incredibly fast, carrying enormous energy. Remember the rule: faster wiggle means more powerful light. An X-ray wiggles so fast and hits so hard that it can punch right through soft flesh, while denser bone blocks it. That is why bones show up as shadows on the film. The light passes through the soft parts and gets stopped by the hard ones. Where does this fierce light come from? From electrons taking especially violent falls. Deep inside heavy atoms, close to the packed center, the energy ladders are enormous, with huge gaps between the rungs. When an electron falls across one of those giant gaps, it releases a photon with far more energy than any visible light. That high-energy photon is an X-ray. Bigger fall, mightier light. To make X-rays in a hospital, machines fire a stream of fast electrons at a metal target. The electrons crash into the metal and knock its inner electrons around, and as everything settles, X-rays come pouring out. Doctors aim that beam through your body and catch the shadows on the other side. In seconds, they can see a cracked bone, a swallowed coin, or a shadow in a lung without a single cut. But this power comes with a warning. X-rays carry so much energy that they can damage the living cells they pass through, breaking delicate machinery inside them. A little now and then is safe, which is why the technician steps behind a shield and drapes a heavy apron over the rest of your body. Too much would be dangerous. The same rays that let us see inside a person can also harm them, so doctors use them with great care. Picture a crowd of people gently tossing beach balls, which bounce off anyone they hit. That is visible light. Now picture the same crowd firing baseballs at full speed. Most sail clean through a paper wall but stop dead against a brick one. That is an X-ray, powerful enough to pass through your soft parts and slam to a halt against bone. There is another way to make this piercing light, and it does not need any falling electron at all. Instead, you simply take a speeding electron and force it to stop. In that sudden, brutal halt, it screams out a burst of light. Slam on the brakes hard enough, and even a tiny particle will scream out light as it stops. We have watched light born from electrons falling down ladders inside atoms. But there is another way to squeeze light out of an electron, and it cares nothing about ladders. It works on one simple idea. Whenever you force a charged particle to change speed suddenly, it throws off light. Speed it up, slow it down, or bend its path, and it sheds energy as a flash of photons. Focus on the slowing down version. Picture a single electron racing along at tremendous speed, carrying a load of energy in its motion. Then it flies close to the heavy center of an atom. The atom's core yanks on it and drags it off course, forcing it to slow and swerve hard. In that violent braking, the electron loses a chunk of its motion energy, and that lost energy has to go somewhere. It flies off as a photon. Scientists gave this a blunt German name, Bremsstrahlung, which means braking radiation. It is light made purely by stopping. The harder and faster the electron breaks, the more energy it dumps, and the more powerful the photon it spits out. Slam an electron to a halt violently enough, and the light it screams out can be an X-ray, strong enough to see through skin. This is actually the second secret inside those hospital X-ray machines. When they fire fast electrons into a metal target, some electrons plunge close to the atomic cores in the metal and get whipped to a stop. Every one of those sudden stops flings out a burst of breaking light. The machine is, in part, a device for slamming electrons into a wall so hard they cry out in X-rays. Here is the key point that ties it to everything before. The light comes straight from the electron's motion. Before the crash, the energy lived in the electron's speed. After the crash, that same energy lives in the photon. Nothing was created from nothing. Motion energy simply changed its coat and became light, the same trade we keep meeting on this journey. You can feel a soft version of this every day. When you slam the brakes in a car, the car's motion energy turns into heat in the brake pads, sometimes enough to make them glow red. A braking electron does the same thing, only its lost motion comes out as pure light instead of heat. Picture a race car speeding down a track, then suddenly forced into a screaming, tire-smoking stop. All that built-up energy has to escape somewhere in an instant, bursting out as heat, smoke, and noise. Now shrink that scene down to a single electron whipping past an atom. Its screeching stop bursts out as a flash of light. The faster the racer, the more violent the stop, the bigger the burst. This kind of light pours out all across the universe, wherever fast particles get slammed around. It glows out of the hot gas swirling near black holes. It lights up the wreckage of exploded stars. Anywhere charged particles are forced to break hard. Breaking light streams out into space, and breaking is only one way to shake a photon loose from a moving particle. You do not even have to stop it. You can keep it moving at full speed and simply bend its path in a circle, using the invisible grip of magnetism, and it will blaze with a light bright enough to blind. Whip a particle in a circle with a magnet, and it pours out a light so brilliant that scientists build machines the size of stadiums just to catch it. We just saw that stopping a charged particle makes light, but you can also make light without slowing the particle down at all. Just bend its path. A charged particle forced to curve is changing direction, and changing direction counts as a kind of change in motion, so it too must shed energy as light. The tool for bending a charged particle is magnetism, the same invisible force that sticks a magnet to your fridge. Here is the setup. Take an electron flying at nearly the speed of light. Now switch on a powerful magnet around it. The magnet grabs the electron and curves its path into a circle, whipping it around and around. With every bit of that curve, the electron flings off light in the direction it is heading. The faster it flies and the tighter you bend it, the more brilliant the light becomes. Push it close enough to the speed of light, and the glow turns fantastically bright and pours out in a tight, focused beam. Scientists name this synchrotron light after the giant ring-shaped machines they built to make it. These machines are enormous. Some are wide enough that it would take you several minutes just to walk all the way around the ring. Inside, electrons scream around the loop near light speed, bent by powerful magnets, and where they curve, they blast out beams of intense light. Researchers wait years for a chance to use these beams, because synchrotron light is some of the brightest, most useful light humans can make. It can reveal the shape of a single molecule or peer inside a running engine. The energy for all this comes from the electron's motion fed by the machine. The magnet does not add the energy, it only steers. The machine first pumps the electron up to blistering speed, and that stored motion is what leaks out as the glowing beam. Once again, the same trade appears. Motion energy becomes light energy. The electron pays for every flash out of its own speed, and the machine keeps topping it back up. This light does not only come from human machines. The universe makes it on a colossal scale. Out in space, powerful magnetic fields whip charged particles in giant curves, and they blaze with this same light across huge stretches of sky. The tangled remains of an exploded star can glow with it for thousands of years. Some of the light we catch from deep space, from the violent jets shooting out of distant galaxies, is this exact kind of light, made by particles bent around cosmic magnetic fields far larger than our entire solar system. Picture a wet dog shaking itself dry. As it whips its body around, water flies off in the direction of the spin, sprayed outward by the turning. A curving electron sprays light in much the same way, flung off in the direction of its swing. The faster the spin, the harder the spray. So we have now seen light born from bending and from breaking, from motion twisted and motion stopped. Every version so far has obeyed one iron rule. Nothing outruns light. Light is the fastest thing there is, the ultimate speed limit of the universe. Except, in a strange twist, that rule can bend. In certain places, a particle really can outrun light, and when it does, it leaves behind a haunting blue glow. At the bottom of a nuclear reactor pool, the water glows an eerie, beautiful blue, and that glow is the ghost of something breaking the ultimate speed limit. We have been told a hard rule all our lives: nothing can go faster than light, and in the emptiness of space that rule holds perfectly. Light in a vacuum flies at about 186,000 miles a second, and nothing with mass can ever catch it. But there is a loophole hiding in that rule, and it is a wonderful one. Here is the trick. Light only hits its top speed in empty space. The moment light enters a material like water or glass, it slows down. Inside water, light travels at only about 3/4 of its top speed, dragged down as it weaves through all the atoms, and that opens a strange door. Now imagine a tiny particle, blasted out of a radioactive atom, flying into a pool of water at nearly full light speed. In empty space, it could never beat light. But inside the water, light has been slowed to a crawl, while the particle barely slows at all. So the particle moves faster than the light around it, outrunning light in the only way the universe permits. When that happens, something spectacular occurs. The speeding particle builds up a shockwave of light, and that shockwave glows a deep electric blue. Scientists call it Cherenkov light, named after the researcher who explained it. It is the light version of a sonic boom. When a jet flies faster than sound, it piles up the air into a booming shockwave you can hear for miles. When a particle flies faster than light in water, it piles up light into a glowing shockwave you can see. This is the source of that famous glow in the pools where nuclear fuel is stored underwater. The fuel is fiercely radioactive, spitting out particles at tremendous speed. Those particles rocket into the surrounding water, outrun the light inside it, and set the whole pool shining with that unmistakable blue. Workers look down and see a calm pool glowing from within, lit by particles breaking a limit everyone thought unbreakable. The energy for that glow comes from the flying particle, born in the heart of a radioactive atom. As the particle tears through the water and stirs up its blue shockwave, it slowly gives up its motion. The blue light is the particle spending its energy, the same trade we have followed all along. Scientists have turned this glow into a powerful tool. They build giant tanks of water deep underground and watch for tiny flashes of Cherenkov blue. Each flash marks a ghostly particle from space streaking through the tank. By catching these blue sparks, they study the most elusive particles in the universe. Picture a speedboat racing across a calm lake. It outpaces the ripples in the water and piles them into a sharp V fanning out behind it. A particle outrunning light does the same, piling up a wake of light instead of water, and that wake glows blue. We have chased light born from vanishing matter, from falling electrons and from particles that outrun light itself. Every source so far has come from the outer shells of atoms, or from particles racing through space. But the most violent light in the entire universe comes from somewhere far deeper and far more dangerous. It comes screaming out of the tiny core at the center of the atom, and it can pass straight through a wall of solid lead. Deep inside the atom sits a tiny core, and when it stirs, it unleashes the most savage light in the universe. We have spent this whole journey watching electrons make light. Electrons falling down ladders, electrons breaking, electrons whipped in circles. But electrons live in the roomy outer part of the atom. Far below them, crammed into a space thousands of times smaller, sits the atom's core. And that core can make light too, of a kind so fierce it makes an X-ray look gentle. This light is called a gamma ray. It is the same stuff as sunlight and radio and X-rays, just at the very top of the ladder, wiggling faster and hitting harder than any other light there is. A single gamma ray can carry thousands of times more energy than a photon of visible light. It is the heavyweight champion of the entire family of light. Here is where it comes from. The core of an atom, like the electrons around it, has its own set of energy rungs, and the core can get excited, kicked up into a jumpy, unstable state, holding extra energy it wants to shed. When the core drops back down to a calmer state, it spits out a photon to carry off that energy. But the rungs inside the core are spaced far wider apart than the electron rungs outside. So when the core falls, the photon it releases is monstrously powerful. That photon is a gamma ray. Because a gamma ray packs so much energy, almost nothing can stop it. It slices through paper, wood, skin, and muscle as if they were fog. To block one, you need something thick and dense. A wall of solid lead several inches thick can do it, or many feet of concrete. This is why places that handle radioactive material hide their gamma sources behind heavy shields. The light coming off them would tear through a person like a bullet through smoke. That same piercing power can also save lives. Doctors aim tightly focused gamma rays at tumours deep inside the body, burning away cancer that a surgeon could never reach without cutting. The very light that can wreck living cells becomes a scalpel made of pure energy, striking only where it is aimed. Out in space, gamma rays mark the most violent events the universe can produce. When a giant star collapses and explodes, it can fire off a burst of gamma rays so bright that for a few seconds it outshines every other star in its galaxy combined. Some of these bursts have crossed billions of miles of space to reach our telescopes, faint messages from unimaginable disasters that happened before the Earth was even born. Picture the family of light as a single staircase. Radio waves rest on the bottom step, soft and slow. Visible light sits in the middle, the tiny band your eyes can see. And gamma rays stand at the very top, glaring down from a height that makes everything below look calm. Same staircase, wildly different power, all decided by how fast the light shakes. So we have reached the fiercest light there is, born from the trembling core of an atom. But that raises a deeper question. Where does the core get all that energy in the first place? To answer it, we have to look at the force that glues the core together and the enormous vault of energy hidden inside it. The core of an atom is held together by a force so strong that unlocking a sliver of it can level a city. We just saw gamma rays come screaming out of an atom's core. That energy has to come from somewhere, and the somewhere is one of the deepest vaults of energy in all of nature, hidden inside every atom you have ever touched. Start with a puzzle. The core of an atom is a tight cluster of tiny particles packed together. Some of them carry the same kind of charge, and things with the same charge push each other away hard. By all rights, the core should blow itself apart in an instant, yet it holds. Something is gripping those particles together with tremendous force, overpowering the push that wants to scatter them. That something is called the strong force, and it is the most powerful force in the universe, by far. It only reaches across a tiny distance, right inside the core, but within that distance it crushes the particles together and refuses to let go. Holding matter together that tightly takes an enormous store of energy, and that stored energy is the volt. Here is the wild part, and it ties straight back to Einstein. When you weigh a full atomic core, it weighs a little less than the separate pieces would if you added them up on their own. Some mass has gone missing. That missing mass became the energy that binds the core together. The tighter the grip, the more mass turns into binding energy. Every stable core is holding a hidden reserve of energy in its very tightness. Now rearrange that core and you can release some of the volt. Two ways do it. Split a heavy core into smaller pieces, and the pieces end up more tightly bound than before, so extra energy pours out. This is how a nuclear power plant runs, and how the first atom bombs worked. The other way is to fuse light cores together into a bigger one, which also ends up more tightly bound, releasing energy. This is what the sun does. Both paths dip into the same vault of binding energy, and both pay out in floods of energy, often carried away as gamma rays. The amounts are staggering. Splitting the cores in a lump of nuclear fuel the size of your fist can release as much energy as burning many train cars full of coal. That is why a single nuclear plant can power a whole city, and why a small amount of this fuel misused can flatten one. The vault holds that much. Picture a spring compressed to the absolute limit and locked shut, straining to burst free. Now imagine millions of these locked springs, packed into every atom, each one a tiny knot of pure tension. Normally they stay locked forever, silent and stable. But pry one open the right way, and it releases its stored energy in a violent snap. The core of an atom is that locked spring, holding the strongest tension in nature. So the gamma rays from a trembling core are paid for by this vault of binding energy, unlocked when the core settles into a tighter grip. Matter is holding staggering power inside its smallest pieces. But there is one final way to spend matter, more complete than anything we have seen. Splitting and fusing only release a sliver of what matter holds. What if you could spend all of it at once, turning an entire lump of matter fully into light? There is a substance so strange that if it touches ordinary matter, both vanish in a flash of pure light. Everything around you is made of matter, your body, this planet, the stars, but the universe holds a shadowy twin of ordinary matter, a mirror version of every particle, with its properties flipped. Scientists call it antimatter, and it is completely real. We make tiny amounts of it in labs, and a little even trickles down from space and forms inside certain machines in hospitals. Here is what makes antimatter unlike anything else. When a piece of matter meets its antimatter twin, they destroy each other. Both particles vanish completely, wiped out of existence in an instant, and in their place a burst of pure light appears, flying off as high-energy photons, usually gamma rays. All of their matter gone, all of it turned into light. This is the most complete trade in the universe. Remember the sun, which converts a tiny sliver of its matter into energy when it fuses hydrogen. Fusion only caches in a whisper of what matter holds. Antimatter caches in everything. When matter and antimatter meet, the whole of their mass converts straight into energy. Nothing is left behind. It is the most efficient release of energy the laws of physics allow. The numbers are almost unbelievable. If you could take a single paperclip of matter and let it meet a paperclip of antimatter, the light released would rival a large bomb. A few pounds of it, meeting a few pounds of ordinary matter, could unleash more energy than the biggest weapons ever built. Antimatter is the most concentrated fuel imaginable, if only we could make and store enough of it, which so far we cannot even come close to doing. You may have already met this process without knowing it. In hospitals, a certain scan works by placing a tiny bit of antimatter, making material inside the body. As it releases antimatter particles, they instantly meet ordinary matter and vanish, firing off gamma rays. Detectors catch that light and build a glowing three-dimensional map of what is happening inside a living person, tracking things an ordinary scan would miss. Doctors use the flash of vanishing matter to hunt for disease. And here is a mystery that keeps scientists up at night. When the universe was born, matter and antimatter should have appeared in equal amounts, then met and wiped each other out completely, leaving nothing but light. Yet here we are, a universe full of matter, planets, and stars, and people. Somehow a tiny bit more matter survived than antimatter. No one fully knows why. That small leftover became everything that exists. We are the survivors of an ancient near-total annihilation. Picture a positive number and a negative number that are perfect opposites like 5 and -5. Add them together and they cancel out to 0, leaving nothing behind. Matter and antimatter do the same thing, cancelling into nothing, except the energy that held them does not disappear. It escapes as a burst of light. So we have found the ultimate light source, matter fully spent, turned completely into a flash of pure energy. Yet even now a nagging question hangs over everything we have seen. What is a photon actually made of? What is the real, deep thing that light itself springs from? Every photon that has ever existed is a ripple in something invisible that fills all of space. We have chased light back through atoms, stars, and vanishing matter. Each time we found the energy came from some source that made a photon. But we never asked the deepest question of all. When a photon is born, what is it actually a piece of? What is light itself made from? The answer is one of the strangest and most beautiful ideas in all of science. Light is a ripple in a field. And to understand that, set particles aside for a moment and think about the whole of space in a new way. Picture the entire universe filled, everywhere, with an invisible something. It has no colour, no weight, and you cannot touch it. It stretches through every inch of space, through the room you sit in, through the empty gulfs between stars, through your own body. Scientists call it the electromagnetic field. It is always there, silent and still, like the flat surface of a perfectly calm ocean covering everything. Now disturb it. Shake a charged particle like an electron, and it pokes this invisible field, sending a ripple racing outward across it. That travelling ripple is light. A photon is one little packet of that ripple, a bump moving across the calm ocean of the field. When you turn on a lamp, you're jiggling electrons and they are slapping the field and sending ripples in every direction. Those ripples wash over your eyes, and you call it seeing. This changes everything about where light comes from. A photon springs into being the moment the field gets disturbed, born fresh from the field itself, and it melts back into the field when it is absorbed. Light is the field, moving. The source only supplies the shake. The field supplies the substance. And here is the part that stretches the mind. This same idea runs through all of physics now. Electrons have their own field-filling space. So do the particles inside the atomic core. Every kind of particle in the universe is a ripple in its own invisible field. Reality, at its deepest level, is a set of these fields, layered over each other everywhere, trembling. What we call particles are the ripples. What we call empty space is the fields lying quiet. Scientists did not dream up this picture for fun. They tested it, and it became the most accurate theory in the history of science. Predictions built on these fields have been confirmed to a precision like measuring the distance across the country and being right to the width of a single hair. When a theory is that exact, physicists trust that it is telling us something true about how the world is built. Picture the calm surface of a pond at dawn, still as glass. Toss in a pebble, and a ring of ripples spreads out across the water. The ripple is the pond itself moving. A photon is a ripple like that, and the electromagnetic field is the pond spread across the whole universe. So the true home of a photon is this field, everywhere at once. But if the field fills all of space, even the emptiest void, then a wild possibility opens up. Could a photon flicker into being from the field alone, born from what looks like nothing at all? Two magnets push each other apart across empty space, and the thing carrying that push is a kind of ghostly light you can never see. Here is a question you may never have thought to ask. When two magnets repel each other, or when a charged comb lifts a scrap of paper, how does the force get across the gap between them? Nothing seems to touch. Yet one object clearly pushes or pulls the other from a distance. Something must carry that force across the empty space, and that something, physicists say, is light. A hidden, secret kind of light. Remember that a photon is a ripple in the electromagnetic field. It turns out that the same field is what carries every electric and magnetic force. When two charged particles push on each other, they are constantly tossing tiny packets of the field back and forth between them, like two people playing catch. Each toss nudges the other particle. That endless game of catch is the force, and the packets they throw are photons. Ghostly ones. Scientists call these ghostly packets virtual photons. They are strange flickering things. They appear for the tiniest sliver of time, do their job of carrying the force, and vanish again before you could ever catch one. You can never see a virtual photon directly, never trap one in a detector. They live and die in a flash too brief and too hidden to observe. Yet their effects are everywhere, in every magnet, every spark, every atom held together. How can something borrow energy to exist and then vanish? This dips into the wild rules of the very small. Down at that scale, the universe allows a kind of borrowing. A particle can pull a bit of energy out of the field for a moment, so long as it pays it back almost instantly. The more it borrows, the faster it must return it. Virtual photons live on this borrowed time, flickering into being with borrowed energy, then giving it back before the universe notices the debt. This might sound like a fantasy that physicists cooked up, but the picture makes real predictions, and the predictions come true to staggering accuracy. When scientists calculate how atoms behave using this game of virtual photons, their answers match experiments better than almost any prediction ever made. The ghosts are doing something real, even though we can never see one face to face. Virtual photons even leave fingerprints we can measure. They give a tiny extra nudge to electrons inside atoms, shifting their energy by a hair. When scientists measured that shift, It matched the ghostly prediction exactly. Empty space, it turns out, is quietly humming with these flickering packets, born from borrowed energy, carrying every force that shapes the world. Picture two boats floating side by side on calm water. One person keeps throwing a heavy ball to the other, and each throw shoves their own boat back a little, while catching it shoves the other boat too. To someone who cannot see the ball, the two boats just seem to push each other apart across the water by magic. Virtual photons are that unseen ball, thrown between charged particles, carrying a force that looks like action across empty space. So light does far more than let us see. A hidden version of it reaches across every gap in the universe, gluing charges, driving magnets, holding the world together. And these ghost photons hint at something staggering about empty space itself. The void is quietly seething with energy, always trembling, always awake. Take a box, pump out every atom, every speck of light, every trace of matter, and the empty space left inside will still be humming with energy. We picture empty space as the ultimate nothing, a perfect void, silent and dead, holding zero of everything. For a long time, scientists thought so too, but the deeper they looked, the more they found that empty space is secretly alive. It seethes, it flickers, it holds a restless energy that never switches off, even in the coldest, emptiest place imaginable. Here is why. Remember those invisible fields that fill all of space, the ones whose ripples are particles? Down at the smallest scale, these fields can never sit perfectly still. The rules of the very small forbid it. Even in total emptiness, the fields quiver with tiny random shivers, like the surface of a pond that trembles no matter how calm the day. Out of these shivers, ghostly particles flicker into being and vanish again in a blink, everywhere, all the time. Empty space is a boiling sea of these fleeting flickers. This constant background hum has a name. Scientists call it the vacuum energy, or the zero-point energy, because it is the energy that remains even when everything has been removed and the temperature is pushed as low as the universe allows. It is the energy of nothing. And that idea should feel impossible, yet experiments confirm it is real. The proof is beautiful and simple. Take two smooth metal plates and hold them extremely close together in a vacuum, almost touching. The flickering of empty space is slightly weaker in the narrow gap between them than in the open space outside. That tiny difference creates a real, measurable push, gently shoving the plates together with only supposedly empty space between them. Scientists have measured this push in the lab. Empty space pressed the plates together. The nothing had force. Here is where it becomes one of the greatest mysteries in physics. When scientists try to calculate exactly how much energy empty space should hold, their answer comes out fantastically, absurdly huge. Yet when they measure how much the vacuum energy actually pushes on the universe at large, it is almost unimaginably tiny. The prediction and the measurement disagree by more than any other number in all of science, so wildly that physicists openly admit they do not understand it. The energy of empty space is both proven real and deeply, embarrassingly mysterious. This restless vacuum may even be shaping the fate of everything. Astronomers have found that the expansion of the universe is speeding up, pushed apart by some unseen energy woven into space itself. Many suspect this mysterious push is tied to the energy of the vacuum, though no one has nailed down the connection. The energy of nothing might be steering the destiny of all there is. Picture the flat, calm surface of the sea, seen from far above. It looks perfectly smooth and still, but drop down close, right to the surface, and you find it never stops trembling, always jittering with tiny motions too small to see from afar. Empty space is like that, smooth and dead from a distance, seething and alive up close. So even perfect emptiness is packed with energy, flickering with ghostly light and phantom particles. And this raises a haunting thought. If empty space itself holds energy, then perhaps there are places in the universe where that hidden energy can be pried loose, where even a black hole, the ultimate trap, might be forced to glow. A black hole is the greatest trap in the universe, a place where even light cannot escape, and yet it may be slowly glowing itself to death. Picture the darkest object nature can build. A black hole is a region where gravity has become so overwhelming that nothing can climb out of it. Get too close, cross the invisible line around it, and you are gone forever. Light that falls in never comes back. It is a pit in space that swallows everything and returns nothing. For a long time, that was the whole story. A black hole only grows. It eats stars, gas, and light, and gives back nothing at all. Then, about 50 years ago, a brilliant scientist named Stephen Hawking did the math and found something that stunned physicists everywhere. A black hole, he showed, should very faintly glow. Here is the strange idea behind it, and it reaches back to the seething vacuum. Remember that empty space everywhere flickers with ghostly particles, popping into being in pairs and vanishing again. Now imagine this happening right at the edge of a black hole at that invisible line of no return. A pair of these flickering particles appears. Before they can meet and vanish as they normally would, the black hole's ferocious gravity snatches one and drags it in, while the other escapes outward into space. The escaped particle carries away real energy, and from a distance, it looks like the black hole is glowing. Scientists call this faint glow Hawking radiation, and it comes with a shocking price. The energy that escapes has to be paid for, and the only account to draw from is the black hole itself. So every time it glows, the black hole loses a tiny bit of its own mass. Bit by bit, over almost incomprehensible spans of time, it shrinks. A black hole is slowly leaking itself away as light, paying for its own faint shine with its own body. For the giant black holes out in space, this leak is agonizingly slow. A big one would take longer than the current age of the universe, multiplied more times than you can picture, to fully fade away. Their glow is so faint that we have never caught it. This idea remains a prediction, elegant and widely believed, still waiting to be seen by any telescope. Still, the meaning is staggering. If Hawking was right, then nothing in the universe lasts forever, not even a black hole. Given enough time, an unthinkable stretch of it, every black hole will slowly evaporate into faint light and disappear. The greatest traps in existence are quietly dying, one ghostly photon at a time. Picture a locked vault sealed so tight nothing can ever get out. Now imagine that, impossibly, one coin at a time keeps slipping through the walls to the outside, and each escaped coin comes straight out of the treasure inside. Given enough centuries, the unbreakable vault empties itself and crumbles. A black hole is that vault, leaking its treasure as light, dying by the slow escape of what it can supposedly never release. So even a black hole can be forced to glow, its energy pried from the trap by the flicker of empty space, and that same idea of light handing over its energy is about to flip our whole journey around. So far we have watched sources make light. Now watch what happens when light itself becomes the source and gives its energy away. Shine the right light on a piece of metal, and it will spit out electrons, as if the light were punching them loose. For our whole journey, we have watched things make light. Atoms, stars, vanishing matter, all pouring photons into the world. Now we turn the story around. Because a photon does not only carry energy away, it can also deliver that energy, slamming into matter and handing over everything it holds. And one simple experiment with this idea cracked open the modern understanding of light itself. Here is the experiment. Take a clean sheet of metal and shine light on it. Under the right conditions, the metal starts flinging out electrons, as if the light were knocking them free. This is called the photoelectric effect. At first it seems ordinary. Light hits metal, electrons pop out. But when scientists looked closely, the details baffled everyone under the old idea that light was a smooth, continuous wave. The puzzle was this: shine a dim blue light, and electrons fly out at once. Shine a blindingly bright red light, far brighter, and nothing happens at all. No electrons, no matter how intense the red glow. If light were a simple wave, more brightness should always mean more punch. But brightness was not the key. Colour was. Only light past a certain colour could knock electrons loose, however faint, while gentler colours failed however bright. A young Albert Einstein solved it, and the answer won him a share of the greatest prize in science. Light, he said, arrives in tiny packets, in photons, each carrying a fixed dose of energy set by its colour. A single blue photon carries a hard punch, enough to knock an electron free in one hit. A red photon carries a soft punch, too weak to free anything, and piling on millions of soft punches never adds up to one hard one. Each electron gets struck by one photon at a time, so the colour of each punch is what matters. This was the moment light's split personality became undeniable. Light travels and spreads like a wave, yet it lands and delivers its energy like a stream of tiny bullets. The photoelectric effect proved the bullet side beyond argument, and it locked in the idea of the photon for good. The whole strange picture of light we have followed was born in part from watching metal spit out electrons. And this trick is everywhere in your life now. The solar panels on rooftops run on exactly this. Sunlight strikes the panel, each photon knocks an electron loose, and the flood of freed electrons becomes an electric current that powers homes. The camera in your phone works the same way, catching photons and turning them into little jolts of charge that build a picture. Every selfie you take is the photoelectric effect, quietly at work. Picture a row of coconuts sitting on a shelf. You can throw 1,000 soft foam balls at them all day and never knock one off. But throw a single hard baseball and a coconut flies. 1,000,000 gentle hits accomplish nothing that one solid hit can do. Photons work the same way. One photon of the right energy frees an electron, while an ocean of weaker ones leaves it sitting there. So a photon can spend its energy handing it to an electron in a single blow. And nowhere is that gift more important than in a quiet green machine that has been catching sunlight and storing it for billions of years, feeding nearly every living thing on Earth. A blade of grass is quietly performing a trick that every factory on Earth would kill to copy. It catches sunlight and stores it. Step outside and look at anything green: grass, a tree, a weed in a crack. Each leaf is a tiny, silent machine running on light. Right now, in every green thing around you, sunlight is being caught, trapped, and locked away as stored energy. This process feeds almost every living creature on the planet, including you, and most people walk past it without a glance. The process is called photosynthesis, which simply means building with light. Here is how it works, in plain terms. A leaf is packed with a green substance that is fantastic at catching photons. When sunlight lands on it, that green catcher grabs the light's energy, the same way we have seen atoms grab photons all along. But instead of just flashing the energy straight back out, the plant does something clever. It uses that captured energy to build. With the energy from sunlight, the plant takes two cheap, common ingredients, a gas from the air and water from the soil, and stitches them together into sugar. That sugar is food. Packed with the sun's energy now locked inside its chemical bonds, the plant has taken fleeting light and frozen it into a solid, storable form: sunlight, caught and canned. And as a bonus, the process breathes out the oxygen that fills our air and keeps us alive. This is the true foundation of nearly all life. When you eat a vegetable, you're eating stored sunlight. When you eat meat, the animal ate plants, so you're eating stored sunlight one step removed. The energy powering your muscles as you read this was, a short while ago, a photon flying through space from the sun. A leaf caught it, a plant stored it, and now it is you. Almost every meal on Earth traces back to light captured by something green. It goes even deeper. The coal, oil, and gas we burn for power are the buried remains of ancient plants and creatures that lived long ago, holding sunlight they captured millions of years back. So when a car engine roars or a power plant hums, it is often burning sunlight that a plant caught before the age of the dinosaurs. Our whole modern world runs in large part on very old stored light, and plants do all this with a quiet grace that shames our machines. They make no noise, no smoke, no waste. They run on nothing but light, air, and water, and they have been perfecting this trick for billions of years, far longer than animals have existed. Life learned to drink the sun long before it learned to walk. Picture a solar panel that can also grow, heal itself, and make copies of itself, all while producing food and breathing out fresh air, powered by nothing but sunshine and a sip of water. No factory has ever built such a thing, yet a single blade of grass does it without a sound. Every leaf is a living machine for catching light and storing it away. so a photon's energy can end its journey locked inside a leaf, feeding the living world for years. We have now followed light from its birth to its capture, but there is still a deep secret in how a photon's energy can change, all on its own, simply by passing through the pull of gravity. Fall toward a heavy object, and a photon grows stronger. Drop a photon toward a heavy object, and it gains energy as it falls, turning bluer on the way down. We have treated a photon's energy as something set at birth, fixed by its colour when the source made it. But a photon's energy can change on the way, without anything touching it, purely because of gravity. This is one of the eeriest truths in all of physics, and scientists have measured it right here on Earth. Start with what gravity does to ordinary things. Drop a ball off a building, and it speeds up as it falls, gaining energy from the fall. Gravity pours energy into anything that drops toward a heavy object. That much feels familiar. Now here is the twist. Gravity does the same thing to light. A photon falling toward a heavy object also gains energy on the way down. But a photon cannot speed up, because it already moves at the one fixed speed of light, always, and it can never go faster. So when gravity feeds it energy, that energy has to show up somewhere else, and it shows up in the photon's colour. Remember, a photon's energy is its wiggle speed, its colour. So as the photon falls and gains energy, its wiggle speeds up. It shifts toward the blue end, growing stronger and higher in energy. Scientists call this a blue shift. The light falls, and it turns bluer. The stronger the gravity, the bigger the effect. Near the Earth, it is real but tiny, far too small to see with your eyes. Scientists had to build a fantastically precise experiment in a tall tower to catch it. They sent light down from the top to the bottom, a drop of just a few dozen feet, and measured that the light arrived very slightly bluer than it left, exactly as the theory predicted. Light gained energy just by falling the height of a building. The universe agreed with the math to the last decimal. Near truly monstrous objects, the effect becomes violent. Picture light falling toward a black hole, where gravity is beyond extreme. A photon plunging in gains enormous energy, its colour shifting wildly toward the blue and beyond, growing more powerful the closer it falls. Gentle light, drawn toward such a place, can arrive as savage high-energy radiation, whipped up to fury by the fall alone. This tells us something profound. A photon's energy belongs partly to the gravity around it. Gravity can pour energy into it or, as we will see next, drain energy out of it. The light itself does nothing but ride the gravity, gaining on the way down like a ball rolling into a valley, its colour the meter that shows the change. Picture a marble rolling down into a deep bowl. As it drops toward the bottom, it rolls faster and faster, picking up energy from the descent. A photon falling toward a heavy object does the same, except it cannot roll faster, so it turns bluer instead. The colour is the photon's speedometer, and gravity is pressing the pedal, so light grows stronger as it falls into gravity, gaining energy from the drop. But every fall has an opposite. If a photon gains energy plunging down toward a heavy object, then a photon climbing away from one must pay a price, and that price will lead us to a puzzle that troubles physicists to this day. A photon climbing away from a heavy object grows weaker and redder, losing energy with every mile it rises. We just watched a photon gain energy by falling into gravity. Now flip it around. When a photon has to climb away from a heavy object, fighting against its pull, the journey costs energy. And the photon pays that toll out of its own pocket. It rises, it weakens, and it turns redder. Think again about the everyday version. Throw a ball straight up and it slows as it climbs, losing energy the whole way against gravity's pull. Light climbing away from a heavy object faces the same tax, but once more, the photon cannot slow down, because it is locked to the one speed of light forever. So the energy it loses comes out of its colour instead. Its wiggle slows, and it shifts toward the red end, growing gentler and lower in energy. Scientists call this a gravitational redshift. The light climbs, and it turns redder. On Earth, this is real, but faint. Light escaping upward from the ground loses a whisper of energy as it rises, reddening by an amount far too small to notice. Yet it matters more than you might think. The satellites that run the maps on your phone orbit high above us, where Earth's gravity is weaker. Because of gravity, Light and time tick along at slightly different rates up there than down here. If engineers ignored this, the dot showing your location would drift off by miles within a single day. Your directions work because scientists carefully account for how gravity tugs on light and time. Now crank gravity up to the extreme, near a black hole, and the redshift becomes monstrous. Imagine light trying to escape from just outside the edge of one. It claws its way upward against savage gravity, losing energy the whole climb, reddening more and more. Right at the edge, the pull becomes so total that the light loses all of its energy trying to escape. It reddens away into nothing and never gets out. That is the very reason a black hole looks black. Light that tries to leave is drained of everything before it can go. Here a sharp question surfaces, and it will haunt the rest of our journey. When a photon climbs away from gravity and loses energy, where exactly does that lost energy go? We have leaned on one law over and over through this whole story. Energy is never destroyed. It only changes form and passes along. So the energy the photon surrenders as it climbs has to end up somewhere. It cannot simply wink out of existence. Picture a hiker climbing a steep mountain. With every step up, they burn energy from their body, growing tired, spending their strength to gain height. A photon climbing out of gravity is that hiker, spending its energy to rise, growing redder and wearier as it goes. But a tired hiker's energy is easy to trace. It went into heat and height. For a climbing photon, the answer runs subtler and stranger. So light loses energy climbing out of gravity, reddening as it fights upward. That surrendered energy has to go somewhere. To follow it, we first have to understand the deepest reason energy is conserved at all. A reason discovered by a mathematician whose name too few people know. The reason energy can never be destroyed was uncovered by a woman whose brilliance the world almost ignored, and her discovery hides a loophole. We keep trusting one rule above all others. Energy is never created or destroyed. It only changes form. We have watched it hold true through fire, stars, atoms, and gravity over and over. But have you ever stopped to ask why? Why should the universe bother to keep its energy books perfectly balanced? What law forces it to? For a long time, energy conservation was simply a fact that always seemed to work, with no one knowing the reason beneath it. Then, about 100 years ago, a mathematician named Emmy Noether uncovered the answer. And it is one of the most beautiful truths in all of science. She proved that conservation laws come from symmetries, from things about the universe that stay the same. That sounds abstract, so here is what it means for energy. Noether showed that energy is conserved because the rules of physics stay the same over time. The laws that govern the universe today are the exact same laws that governed it yesterday, and the same that will govern it tomorrow. Do an experiment now or a year from now, and nature behaves identically. Because time itself does not change the rules of the game, energy stays balanced. The steadiness of the laws across time is the deep reason the books always add up. Sit with how strange and wonderful that is. The reason a spark of chemical energy can become heat, then light, then warmth in your skin, all without a single unit going missing, is that the universe plays by the same rulebook at every moment. Energy conservation is the shadow cast by the unchanging steadiness of physical law. So now return to our climbing photon, reddening as it fights out of a star's gravity, losing energy. Where does that energy go? Here, near a star or a planet the books balance cleanly. The photon banks its lost energy into the gravity between it and the heavy object, the same way a ball climbing upward stores its lost motion as height. Nothing is stolen. The photon and the gravity simply trade, and the total holds steady. Noether's rule is safe because near a star the setup stays the same over time. But look closely at what that safety depends on. Energy stays balanced only as long as the rules, and the stage they play out on holds steady over time, and that plants a chilling seed. What if there were a place where the stage itself refused to hold still? A place that is genuinely different tomorrow than it is today, growing and changing on the grandest scale. In such a place, Noether's guarantee would crack. Energy conservation, the rule we have trusted through this entire journey, could quietly fail. Picture a shopkeeper whose books always balance, penny for penny, because the prices in the store never change from day to day. Steady prices, honest books. But if the prices began shifting every single day, growing and stretching without pause, the accounts would stop adding up, and money would seem to appear and vanish from the ledger. Energy is the money. Steady physical law is the fixed price. And there is one place that behaves exactly like a store with ever-changing prices: the universe as a whole. To reach it, we have to find the oldest, most stretched out light there is, a glow left over from the birth of everything. Everywhere you look in the sky, in every direction, a faint glow is shining, and it is the oldest light in all of creation. Point a radio telescope at the darkest, emptiest patch of night sky, far from any star or galaxy, and you will still catch a signal. A faint, steady hiss of light, coming from everywhere at once, filling the whole sky evenly. For a while, the scientists who first found it thought it was a glitch in their equipment. They even cleaned bird droppings out of their antenna, sure something was wrong. But the glow would not go away. It was real, coming from the entire universe. This glow is the oldest light there is. To understand it, we have to go back to the very beginning. The universe was born long ago in an unimaginably hot, dense state, and it has been expanding and cooling ever since. In its first stretch of time, the whole universe was a blazing fog, so hot and so crowded that light could not travel freely. Every photon was trapped, bouncing among the packed particles, unable to fly. The entire universe glowed like the inside of a star, a solid wall of light going nowhere. Then, as everything expanded and cooled, a turning point came. The fog thinned. The particles calmed and joined into the first simple atoms, and all at once, across the whole universe, the fog cleared and light broke free. For the first time, photons could fly in straight lines across space, released everywhere at the same moment. That flash of freed light poured out in every direction, and it has been travelling ever since. That ancient burst of light is what we still catch today, coming from all over the sky. Scientists call it the cosmic background glow. It is a baby picture of the universe, a snapshot of the exact moment light was first set loose, billions of years ago. When you look at it, you are seeing farther back in time than any star or galaxy in existence. You are seeing almost to the beginning. Here is what should give you chills. This glow is all around you right now, passing through your body every second. It even leaks into everyday life. Old televisions that showed static between channels were catching a tiny bit of this ancient light in their snow. A sliver of that fuzzy hiss on an old screen was the glow of the newborn universe, arriving in your living room after a journey of billions of years. But something has happened to this light on its long trip. When it first broke free, it was fierce and hot, a brilliant blaze pouring from a universe glowing like fire. Yet today, when we catch it, it is feeble and cold, a faint whisper of microwaves barely above the coldest possible temperature. The oldest light in existence has been drained of nearly all its strength. Something bled its energy away across the ages. Picture a photograph of yourself as a newborn baby, taken the very first instant you entered the world. That single picture captures a moment you can never see any other way. The cosmic glow is that photo for the entire universe, the first light ever set free, still crossing the sky to reach us. So the oldest light has arrived, exhausted and cold, a shadow of the blaze it once was. Something stole almost all of its energy on the way, and finding out what did it will finally bring our whole journey to its strangest and deepest answer. The oldest light arrived cold and weak because the universe itself has been stretching it thinner for billions of years. We have seen two ways to change a photon's energy so far. Gravity can pour energy into falling light, or drain it from climbing light. But the ancient glow of the newborn universe lost its energy in a completely different way, and it is the strangest way of all. This time, no gravity and no passing object stole its energy. The growing of space itself drained it. Here is the idea that changes everything: space can stretch. And ever since the universe was born, space has been expanding, growing larger in every direction, carrying the galaxies farther apart like dots on the surface of a balloon that someone keeps inflating. This expansion is real and measured. The universe is bigger today than it was yesterday, and it will be bigger still tomorrow. Now think about a photon flying across this stretching space for billions of years. Remember, a photon is a wave with a certain wiggle length. As the photon travels, the very space it is moving through is expanding beneath it. And as space stretches, it stretches the photon's wave right along with it. The wiggle gets pulled longer and longer, drawn out by the growing universe. A longer, slower wiggle means lower energy and a redder colour. So the light loses energy simply by travelling through expanding space. Scientists call this the cosmological redshift. This is exactly what happened to the ancient glow. When that light broke free, it was fierce and hot, wiggling fast and carrying huge energy. But it has been flying across space for billions of years, and all that time, space has been stretching. The light's wiggle got pulled out longer and longer, stretched by an enormous amount, until its once fierce blaze faded into the feeble, cold microwaves we catch today. The universe did more than carry the light. It drained it, by growing around it the whole way. The farther light has travelled, the more it has been stretched. So when astronomers look at distant galaxies, they see their light shifted toward the red, and the more distant the galaxy, the redder its light. By reading how stretched a galaxy's light is, scientists can tell how far away it sits. The redshift became a cosmic ruler and a cosmic clock, letting us measure the size and age of the universe itself. Reading stretched light, scientists worked out that the universe is nearly 14 billion years old. But this quietly drops us in front of the deepest puzzle of the entire journey. When gravity drained a climbing photon, we could follow the lost energy. It banked cleanly into the gravity and the books balanced. This is different. This photon lost its energy to the stretching of space itself. So where did that energy go? Picture a short, tight wave drawn on a deflated balloon. Now blow the balloon up bigger and bigger. The drawing stretches with the rubber, and that tight little wave gets pulled into a long, lazy one. The photon is that drawing. Space is the balloon. And the growing balloon stretches the light thin, so the ancient glow was drained by the stretching of the cosmos. Trillions upon trillions of photons across the whole universe have all lost energy this way. That is a staggering amount of missing energy. And when scientists ask the simple question, where did it all go? They run headlong into a mystery that shakes the most trusted law in physics. The most trusted law in all of physics, that energy can never be destroyed, quietly bends when you look at the whole universe. We have arrived at the strangest idea in this entire journey. Across the cosmos, countless photons have been losing energy for billions of years, drained by the stretching of space. Multiply the fading of the ancient glow by every ray of light crossing the universe, and you get a colossal amount of energy that has gone missing. So the question is simple and enormous. Where did all that energy go? Bring back Emmy Noether's beautiful rule. Energy stays balanced only because the rules and the stage of the universe hold steady over time. As long as tomorrow works the same as today, the books add up, and no energy can vanish. It leans entirely on the universe staying the same across time. Now here is the crack. The universe as a whole does not stay the same across time. It is expanding. It is genuinely bigger tomorrow than it is today, changing on the largest scale there is. The stage itself is growing. And that is exactly the condition Noether warned about, the one place where her guarantee comes undone. When the universe changes over time this way, the tidy law of energy conservation stops applying to the universe as a whole. So what really happens to the energy that redshifting light loses across the cosmos? The startling answer many physicists give is that it simply is not conserved. On the scale of the whole expanding universe, that energy is not required to go anywhere at all, because the rule that would force it to balance no longer holds. The energy of the ancient glow was not banked into gravity, and not hidden in some new form. In a real sense, it was lost, drained away by expanding space and never repaid. This unsettles people the first time they hear it, and it should. We are taught energy conservation as an unbreakable law, never violated, and inside any lab, on any ordinary scale, it holds perfectly, tested countless times. But stretched across the entire growing universe, the law loosens its grip. Physicists still discuss how best to describe this, and some prefer to draw the books differently. Yet the honest, widely shared view is striking. On the grandest scale, the universe does not keep its energy books balanced the way we thought. Every photon we followed carried energy, and we traced that energy back to some source, always trusting it could never truly be created or destroyed. Through fire, stars, atoms, and gravity that trust held. But at the edge of the cosmos, watching ancient light fade as space grows, even that bedrock law bends. The universe, it seems, does not owe its energy back. Picture a bank that always balances every account as long as the rules of money never change. Now imagine the rules of money themselves slowly shifting every single day, forever. In such a world, cash could simply fade from the vault and no law would be broken because the rules that once forced balance have dissolved. The expanding universe is that shifting world, and fading starlight is the vanishing cash. So a photon's energy can be born from many sources, and, at the larger scale, it can quietly slip away into nothing at all. We have chased light from a candle to the birth of the cosmos. Now it is time to gather everything we have found and answer the question we began with. Where does a photon's energy truly come from? So where does a photon's energy truly come from? After this whole journey, the answer runs deeper and stranger than we ever guessed. We started with something simple. Light hits your skin, and it carries energy. That energy had to come from somewhere, so we chased it, backward, through the whole universe, and along the way we found a whole family of sources, each handing energy to light in its own way. We found energy poured into light by heat, as shaking atoms glowed, by chemistry, as fuel released its stored springs in a flame, and as a leaf froze sunlight into food, by electricity, driving a wire to glow and a sign to shine, by motion, as breaking and bending particles flung out photons, by gravity feeding falling light and draining climbing light, and, most extreme of all, by matter itself, vanishing in the core of a star or meeting its antimatter twin, turning pure substance into a flash of pure light. But underneath every one of these we found something deeper. A photon is a ripple in a field, an invisible ocean that fills all of space. The source, whatever it is, only supplies the disturbance. It shakes the field, and the field answers with light. So the truest home of a photon's energy is that field, everywhere at once, waiting silent until something stirs it. When you ask where a photon comes from, the deepest answer is that it rises out of the field itself. And we learned one more thing, the hardest of all to accept. For almost this entire journey, one law held firm. Energy is never created or destroyed, only handed from form to form. It survived every test we threw at it, through fire and stars and gravity. Yet at the very edge, watching the oldest light fade as space stretches, even that law softened. On the scale of the whole growing universe, energy can quietly slip away, owed back by no one. The books that always balanced finally stopped adding up. So a photon's energy comes from a source. Yes, always. But that source is only borrowing and reshaping something deeper, a ripple lifted out of an invisible field, obeying a law of balance that itself bends at the boundary of the cosmos. Light is a message, and behind every message lies a whole hidden machinery of fields, forces, and vanishing matter that most people never glimpse. Here is why this should matter to you. The next time sunlight lands warm on your face, you will know what you are truly feeling. The ghost of vanished matter, born in a furnace hotter than you can imagine, trapped for ages, freed at last, sent racing across 93 million miles of space, all to end its long life against your skin. That warmth is the corpse of a tiny piece of a star, delivering the last of its energy to you. Every ray of light around you carries a story like that. The glow of a screen, the flicker of a candle, the faint hiss of the newborn universe passing through your body right now. Each one is energy on the move, lifted from a hidden field, spent and reshaped and passed along, tracing back through the deepest laws of reality. Light is how the universe hands its energy from one place to another, and now, when you look at it, you will see the whole invisible journey behind the glow. Look up, the sky is full of it.